Okay, so if you are in here right now, and I expect you are in lecture group number 1, okay? If your name is not listed in lecture group number 1, then it's not anticipated that you'll be here on Mondays rather. Lecture group number 1 is going to come to Monday's lecture. Lecture group number 2 is going to come to Wednesday's lecture. I have decided that I'll repeat the same lecture on both days. And as a result of that, we'll have about half as many lectures as we normally would. And so that's why it's very important that you stay up on your reading, okay? I know you didn't have the opportunity to see all of what I was talking about during the video from last Wednesday. Hopefully I've got that fixed now. Fingers crossed, there's no way to know until after it's over. But you should be aware that you have a course for 420-01 on Canvas, okay? You should already have come here. You should already have seen and read the course syllabus because we went over it in the lecture, which I know you watched from Wednesday. And I expect that you have watched that lecture already. That'll be the one time where I don't repeat the same information twice in a week, okay? So if you haven't seen that lecture already, then you have missed out on the basic introductory stuff to how we're going to do things this semester in this course, okay? So you're going to want to go back and look at that lecture. You're also going to want to review the syllabus, which has some important information about it. I know you have, here's where lecture 1 is linked from, okay? This is all the information about lecture 1, including the video, my lecture notes, and the notes that I displayed in class, so sort of the whiteboard notes. And that's the process by which we're going to go ahead and do that this semester. Instead of me getting up and trying to record the whiteboard, I'm going to be making use of a technology called Jamboard, which allows me to, assuming I can click because this is not going to be in the way the whole time. Interesting. All right, so it allows me to show you a whiteboard and then edit on my tablet. Okay. And these whiteboards are going to get saved and be displayed from class to class. Okay. So I know you're already aware of all that, but I want to touch the high points again. You're also aware that we're using a Zybook book for this semester. All right, so the online textbook, and I know you've already gotten access to that. And you are additionally aware that there is an outstanding reading assignment for Chapter 1 in that Zybook, which is due August 27th, which is 3 days from now. And I know you've already started, or at least started to think about how you're going to tackle that, okay? You're going to read that book, and the book is set up so that it has programming, or rather participation activities throughout the lecture content, throughout the chapter content, the material in the book. And you interact with those participation activities to sort of reinforce what the book has been talking about and what the lectures will be talking about. That is automatically linked back through Canvas. So the work that you do there in completing those participation activities, the percentage of them that you get done counts as a component for your final grade as calculated in the Canvas course, right? All that's laid out in the syllabus, which again, I know you've already seen, okay? So, but I just, for the few of you who may not have, I wanted to point that out. Additionally, virtual office hours will be held via Zoom, all right? I had them this morning, and this afternoon. I'll have them Wednesday morning and Wednesday afternoon. The information for that and how to get in contact with me via Zoom at any time during office hours is linked on that link right there. There's a page that gives you that information. And that information is also duplicated to some degree in the syllabus, although the specifics of how to access the Zoom meeting that I'll be using are listed here. Otherwise, if you want to get in contact with me, send me an email, and if we need to, we can set up a Zoom meeting at any point, even outside of the office hours. Okay? So if any of that is new information to you, then you are behind. If that was new information to you, then it's not too late to catch up. It just means that after class today, you need to go back and look at the lecture, look at all that information that's been available to you since last week on Canvas, because what we're going to do today is we're going to move on into some new material. Any questions before we do that? Yes, ma'am.
If you were going to do only one lecture per week, are you going to record the second one and upload that?
I am, yeah. Yeah, and I'll probably post them both. Reason being that that gives us some insurance against something happening against one lecture. And I might not cover 100% the exact same thing. I certainly won't say the exact same thing in both things. So you're only responsible for your lecture, right? You don't need to see the other class's lecture, except for this one case from last week, okay? And so that's how I think we're going to do it. I considered pushing through and having multiple lectures per week. I am doing that in some classes, but I think for this class, since it's a 400 level class and you guys are all pretty mature, and I expect you to be able to stay up with the reading, I'm just going to do one lecture covering the most important stuff per week. And then additional, I'm already planning to have a supplementary lecture video up later this week, which will explain your first assignment or your first exercise, which will be due next week at some point. So keep an eye out for that. Okay. Other questions? Okay, so what we were talking about last time is we were trying to orient the operating system we're trying to say what the OS is, okay? What is the, or even an operating system, okay? And we began by first asking the question, what is a computer? And that led us to talk about all the different things that a computer can be, okay? But first and foremost, this has to do with abstraction. Okay? Someone want to give me a definition just off the cuff of what abstraction means? To have the details, to hide the details. Okay, yeah. Yeah. Anybody else want to take a stab at it?
You don't have to see everything.
Okay. Okay, I think you guys are on the right track. The notion is that I can treat a complicated entity, which is composed of many smaller, less complicated entities, as if it is an atomic whole, right? And not have to worry about how the smaller composing entities are engineered, structured, whatever, okay? So the operating system and everything to do with computers is about abstraction, okay? But the operating system is no different. The operating system is about the notion of abstraction, okay? It's common to have a couple of common metaphors get used when you're talking about operating systems. This is true in your Xi book. This is true in the other books that I've used when teaching operating systems. And they are that the operating system is a resource manager and that the operating system is a quote-unquote bridge. Okay? But what kind of resources does the operating system manage? Where we left off in the lecture from Wednesday, where we left off from the lecture on Wednesday is we finally got to the kind of computer that does multi-programming. Okay? And a multi-programming computer is a computer that appears to run multiple programs at the same time. Okay? And why do I say it appears to run multiple programs at the same time?
Process can only handle one instruction at a time.
Because a processor can only execute one instruction at a time, right? What is a program? Well, it is a bunch of processes. What are processes? Well, we'll talk about that because that's one of the things that operating system has to deal with, right? But a process at their heart is data and the instructions that are being done on that data, okay? And I mean instructions at the level of machine language, okay? The processor can only execute one instruction at a time, okay? But if we have, so how do we then have multi-programming computers? How do we make it look like computers are executing multiple processes at a time? Now, what is the computer in front of you doing right now? What is the computer up here? What's my computer doing right now? How many things does it appear to be doing? It's recording a video. Zoom is running, right? I'm in a browser. Okay, I've got multiple tabs open in that browser, right? And not only that, but if I look at the task manager, I have no idea what that's going to do to Zoom. But if I look at the task manager, right, then you can see all these processes are active in the background. Most of them are not doing anything, but you can see that some of them are using percentages of the CPU. Okay? Hundreds of concurrent processes are running at any given time on modern machines. Okay? Yet, the processor can only ever manage to run one instruction from one process at a time. Okay? It is the job of the operating system to manage resources for the purposes of appearing to run multiple processes at a time. Okay? The reason why it looks like multiple processes are running at a time is because processor time is a lot different than user time. Okay? It takes users a long time to do anything. It takes processors very short amounts of time to do a great many number of things. Okay? And so while the program is waiting for user input here, okay, it's not doing anything. It has nothing to do, right? So the processor needs to be told, don't wait on this, go do something else, okay? And so the job of the OS is to interleave the processor resources. And that includes not just the processor, but also memory, cache memory, etc., as we'll see, right? To make it look like multiple processes are running at the same time. Okay? They're not, but we need to make it look like they are. The other thing that's sort of the job of the operating system is that comes in when you start to think about how you program the various computers that are out in the world. Okay? In the early days of programming, you programmed for a specific computer with specific peripherals. Okay? Now, if you want to write a program that uses the internet, okay, how many of you have done any socket layer programming in C or C++? Any networking stuff? Okay, one or two. Okay, that's fine. You didn't have to care what network card your computer had. Okay, why? Because all network cards respond to the same instructions from the operating system? No. Or from the same instructions from the processor? No. But because the operating system, and here's this other metaphor that often gets used, is a bridge. Okay? It's a bridge between what two things? It's a bridge between the device management details, right, that are extremely ugly, difficult to deal with, and the user interface details for programming languages. And in this case, user means the programmer. Those are designed to be pretty, be smooth, okay? To not have to worry about the nitty-gritty details about what bits go where when you're discussing how to access your network through a given card. Okay? Between device management and user interface. So monitors are different, printers are different, drives are different. They're made by different manufacturers. Okay? They use different technologies, right? But the operating system provides an abstraction, okay, that makes it look like every monitor can be treated the same. Every drive can be treated the same. Every printer can be treated the same, okay, programmatically, right? Even at the programmer level, yes, but even at the user level, especially, right? File print always works. That's a little bit of a simplification, but it always works because all printers can be treated like they are printers. Okay? The secret is that's not the case. And the bridge between what we perceive and what's true is the operating system. Okay? Any questions about that? You can also imagine, though, that that also feeds back and lets us reevaluate the resource manager tag. Because we said, you know, operating systems are resource managers in that they manage the resources to get it to look like and appear to the user like the computer is running multiple processes at once. Okay? But if you have devices that are being thrown into the mix, okay, what happens is if one program needs to print, okay, then why would you make every other program wait on this one program to print? Okay? No, instead what you would do is you would design your operating system so that the print command goes out to the device, aka the printer, and while that device is working, you put this to sleep and you choose one of these other devices, or one of these other programs rather, to execute. Maybe we choose process 3. Okay? The act of choosing one of these processes is called scheduling. And how an operating system schedules one processor to become active while choosing to make all the other processes inactive is a major component of what we'll be talking about in this class. Okay? So as a resource manager, when you start throwing in tackling the ugly side of devices, then you actually create new opportunities for doing multi-programming, okay? for making a multi-programming device. So there's one other thing that bears mentioning at this point, and that is memory management. Okay. Here's the over-under on the truth about memory. You don't have enough. Okay? You don't have enough. What do I mean by that? Our lives are simple. Our lives are simplified if our computers can keep all programs in RAM all the time. Okay? But you can't because you don't have enough. Okay? So what you need to be able to do is you need to be able to manage the memory that you do have, okay? So that as you're loading and unloading programs, the memory that those programs require is present in active RAM, okay? So you've got this notion of RAM and you've got cache. This is active memory, and this is sort of like the concept of stored memory, okay? We can have lots of this, but we are limited in the amount of this that we have. This is where the processor has direct, quick access to. This is much slower, okay? So with memory, you can always have lots of slow memory or a little fast memory, okay? But we don't have a lot of fast memory, okay? And so we want to allocate the fast memory to the processes that are currently active. In fact, we have to, because if we don't, then we end up with memory that is not accessible by the processor, but is required by the program that is running, that needs to be running, okay? So this notion is also a major topic that we're going to talk about this semester, okay? Things like paging and virtual memory are going to be defined and discussed. Okay? So I've kind of laid out some of the major topics. That we'll see. The first of which is organizing units of processing. And specifically, we'll look at something called processes, and we'll look at something called threads. Okay? Organizing the units of processing. Then we'll look at device management. And we'll look at memory management. Okay? In fact, you can see that roughly, that's how the next couple of chapters lay out for us. Right? Process and threads and resources. I forgot to mention scheduling. Talked about it, but I didn't put it on our list. Okay, this is memory management, and concurrency has to do with a specific kind of memory management. Deadlock also is a specific aspect of memory management. I mentioned virtual memory. Okay, then we'll talk about the file system and the input and output, and then security concerns. We'll kind of round out the end of the semester. Okay. So my objective so far has been to kind of place us into a mindset of understanding what it is that makes an operating system and what kind of components make up an operating system. Okay, because we are not going to take, for the reason that no one can really tell you, no one agrees on what a quote unquote operating system is. That is to say, no one is really sure that an operating system has exactly these components, okay? Because operating systems respond to changes in technology, okay? I'm going to drill down on that in just a second. But what people can say, what we can say for sure, is that these are the fundamental components that every operating system must wrestle with, okay? You've got to wrestle with being able to construct structures that define units of processing. You've got to be able to schedule those units of processing on the processor. You have to be able to manage the memory. Okay? You have to deal with deadlock. Deadlock becomes a problem whenever you're using multi-programming computers. Okay? And we're going to look at each one of those. No matter what you say an operating system is, that operating system will have to manage those key components. Okay? The other way to do an operating system class is to say, we're going to learn how to use a specific operating system, and then we're going to tear it down and we're going to see how it's constructed. Okay? That is not, in my opinion, appropriate for an undergraduate class, because you'll see how one operating system is constructed, but you won't understand the design decisions that went into that design. Okay? And so instead, what we're going to talk about is we're going to talk about the aspects of the design decision which are apparent no matter what operating system you're using. Okay? All right, any questions about anything I've said so far? Any questions? So I said something a minute ago that I want to drill down on. I said that operating systems and what is an operating system changes as technology changes, okay? So I can't tell you exactly what an operating system is, because if I were to have done that 10 years ago, my definition would not match what I would say an operating system is now, and I don't believe it'll match what I say an operating system is exactly 10 years from now, okay? Think of it this way. Before computers entered the electronic age, right? If you guys have seen the video from last week, where they had the wooden computer. Okay, we showed you the wooden computer. That operating system is effectively non-existent. It effectively does not have an operating system, yet it is a computer. Okay. Then someone invents vacuum tubes. Okay. What do we say is the important aspect about a vacuum tube? What is a vacuum tube? It's a switch. And in particular, it is a switch that is off until an electrical impulse turns it on, in which case it is on until an electrical impulse turns it off. Okay? So it's a very early form of electronic switch. Okay? Right? So vacuum tubes led to transistors, which led to ICs, which led to very large scale integration, aka processor chips, which led to networked computers. At every stage, the operating system had a different job. Okay? When it was strictly a vacuum tube, okay, the operating system just did batch jobs. Okay? So we showed in Wednesday's lecture a picture of like a room-sized computer. Okay, and that particular room-sized computer was called the ENIAC. The computers that immediately followed that had devices which could read in punch cards. Okay, and so you would program your computer using not a high-level language, but using machine language. You would punch those machine code opcodes into the punch card, and you'd have a stack of them, and someone would physically walk them over to the punch card reader and put them in. Okay? Now, this is no good, right? Because the bottleneck in running programs like that is where? Having to insert them with the person that has to keep them in order and walk them over there and put them in, right? It doesn't take very much longer before that first happens until the machine is waiting on additional programs. Okay, so the way to manage this, if you're in the vacuum tube and even in the early transistor world, okay, was to have batch systems. And all the batch system did, the operating system, was store programs internally to be run one after the other. Okay, so the operating system took over the job of the person who was in charge of putting one in at a time. Okay, they could put in a bunch at a time, and the operating system would remember, okay, these are the instructions for one program, these are the instructions for another program, these are the instructions for another program, but they all had to be run one after another in sequence. Okay? Then you get transistors that are going into integrated circuits, and you start to be able to do multi-programming. Okay? And so at each turn, as those technologies advanced, the operating system evolved. The notion of an operating system evolved to create sufficiently complex abstractions to reveal the power of the new technology, right? Most recently, we've had networked computers, okay? And operating systems that have been designed and adapted to make it seem like multiple processors working at different places throughout the world are one machine. Okay, what am I talking about? Someone give me an example of that. I've already used it today. I don't know if I showed you. I probably didn't. Where does this exist? Not just one server, right? Maybe it does, but I don't have that guarantee. Okay? I don't know. These are my files that I have on Google Drive. I don't know where in the physical world they exist, and I have no guarantee that they all exist on the same physical machine. They exist in the cloud, which is just a buzzword for somebody else's computer, right? But not just one computer, potentially. A logical computer, okay? Which could actually be just an abstraction for multiple physical computers somewhere in the world. And this is a low-level cloud example. I don't know if any of you have done any application level programming in the cloud, okay? But virtual operating systems that exist in the cloud are a thing, and in reality, they can bring together resources from multiple computers across the globe. And they make it look to the user as if it is just one computer, okay? Which is a very different kind of beast than the sort of thing you generally think about when you think about operating systems. What's the first thing that pops into your mind when I tell you think of an operating system? Okay, Windows, yeah. The world's favorite operating system and my least favorite, yeah. Right? I would even argue that in some ways it's not an operating system at all, but I won't get into the details there, right? The new versions are better at that. But that's the user view of what an operating system is, okay? Just like the user view of what you get when you create an Amazon Web Services account is that you get a computer in the cloud. No, you don't. You get to think that your data and the processing that happens on your data is happening on a computer that you have access to, when in fact, it is distributed across the globe on many different computers, all of which work together to make it look like, hey, there's one, the operating system works with all of those to make it look like there's one computer that you have and it's on the cloud, okay? Regardless of how complex that abstraction gets, you have to wrestle with what processes are running and how are we going to manage the resources for those processes? How are we going to schedule the resources, schedule those processes? How are we going to update the memory so it makes it look to the program that's running that its memory is available to it, even though it's potentially scattered across the globe, right? What do we do in the case of deadlock, et cetera, et cetera, et cetera? Okay? The fundamental problems that face us when we deal with designing operating systems have not changed in 50 years, even though our advances in computer technology have been immense. Okay? And we don't expect them to fundamentally change in the next 50 years, even though I don't know what comes next after cloud computing. Okay? You may say, well, quantum computing is going to change everything. Quantum computing may change a lot of things, but whatever operating system makes it look like a quantum computer is going to have to wrestle with being the resource manager and being the bridge between complicated things and simple interfaces. Okay? And that's what an operating system is, and that's how we're gonna break it down and look at how techniques to handle those kinds of things. Right? One more central idea to talk about. Let's call this a key concept. Is the notion of a kernel. Okay? Has anyone heard that term before? It's probably come up from time to time in various classes, especially depending on what kind of programming you were doing. Does anyone have a definition or kind of want to enlighten us about what a kernel is? Yes, please don't hesitate to tell me that you can't see something because I've got 5 different things I'm juggling right now. So go ahead.
I've got the term kernel a lot on like the Linux.
Okay.
Operating system things.
Yeah, that's absolutely true. It is a term that comes out of the Unix world, and so the term itself is sometimes associated with Unix-like operating systems. But all operating systems have some, even though Windows doesn't maybe use the term kernel, it's got the same, it's got a concept of a kernel. Okay, when you're doing Linux, the Linux kernel is managed by Linus Torvalds, right? And he updates the Linux kernel every once in a while. And then all the distros get the new Linux kernel, and they're all running the same kernel. Okay, kernel, I don't know what we're up to now. I'm making up numbers, 7.13.9 or whatever. Okay, I think it's way higher than that, right? But so that's kind of that is the same concept. But what does the kernel do? Well, first off, we know that it is a system. Okay. In particular, it is a software system. It is the operating system software component. I'm going to give you the book. I'll give you the book definition. The operating system software component that contains all functions for managing the system. Inside the kernel, you will find the most essential services like memory services, device management, creating and managing processes and threads, dealing with units of computation, communication between concurrent system activities. So if one process needs to speak to another process, needs to message another process, then the software that makes that happen is part of the kernel. Okay? It's the sensitive software components that make up the fundamental parts of the operating system. Okay? So you're like, oh, so the kernel is the operating system. Again, that depends on who you ask. It depends on what you mean by operating system. Generally, I would say there is a distinction because the operating system also provides the interface between complex, ugly device management and the pretty user world. Okay? So that's got to be a part of the operating system, but that is not part of the kernel. Okay? We can have a religious debate about that. But in here, kernel and operating system are not the same thing. A kernel is part of the operating system.
Would it be fair to call it a framework?
To call the kernel a framework? It's more like the kernel. And why is it called the kernel, by the way? Outside of the computer world, where do you hear the term kernel? Yeah, right. So the seed of the thing, right? Who else? What does somebody say? Yeah, but not that kind of kernel. It's not a COLNEL or whatever. It's a KERNEL. Okay. Yeah, it's the seed, right? It's like the central part on which frameworks are built. Okay. So it's not the framework itself. The kernel and the framework would be the operating system. But the kernel makes all this as the central part. It is the fundamental thing, it's the fundamental software component that the operating system can use to communicate at low levels with the hardware. Okay? So why then is it a good idea to conceptually separate the notion of a kernel and the notion of the rest of the operating system? Well, what it does is it allows us to divide, okay? We can divide the operating system into 2 parts. We can divide it into kernel mode and we can divide it into user mode. Okay? Kernel mode and user mode. And the reason why we would want to do this is because we want to create a security barrier between applications that are running in user mode and applications that are running in kernel mode, right? When I say security barrier, I just mean a barrier that keeps programs from doing something destructive regardless of intent of the author of those programs, okay? I don't mean just keeps bad, faithless actors from hurting the system, but also keeps incompetent actors from hurting the system. Okay? There's no need to assign malice whenever it's just as likely the fault of incompetence. Okay? Right? And we can stop both malicious activity and incompetent activity by using the same structure. So what this does is, this is the state. So we can now begin to design CPUs that respect these two different states. And what do I mean by CPUs? I mean specifically processors, central processing units, like the chips themselves. Okay? The chips themselves can run in either of these two modes. So depending on how you want to think about it, either the OS implements these two modes and the CPU is designed to run in those two modes, or the CPU is designed to run in those two modes and the OS implements that. Regardless, you get the same effect. Okay, the OS and the CPU are working together. Okay, the CPU might run in kernel mode or might run in user mode, and the OS understands the difference between those two and what can be done in what mode. Okay, user mode has only non-privileged instructions. And kernel mode has both privileged instructions and non-privileged instructions. Oh, I butchered the spelling on that, but you get the idea. Okay? So that leads a question. What is a privileged instruction? And again, I feel like the spelling is wrong there, because it's P-R-I-V-I. I-V-I-L-E-G. No, maybe I'm right. Okay. So what is a privileged instruction? So those would be CPU instructions that perform critical operations, right, that access I/O devices and the CPU's status and control registers. Okay? So instructions that access, modify the CPU's internal state, including but not limiting to its onboard cache memory, as well as accessing any external device. Okay? Now, I said earlier that I anticipated some of you may have heard the distinction between kernel mode and user mode, depending on what kind of programming you've been doing. Maybe none of you have been doing programming where it mattered. Most of undergraduate programming happens in happens directly in the user mode, and if we need to do anything in if we need to run any privileged instructions, we rely on libraries. Okay. With the distinction of what kind of programming. Does anyone want to take a stab at that? Well, yeah, I mean, by definition, yeah. But what's more specifically than that? The word I'm looking for. Oh, you guys got to throw something at me because I'm writing over here and you can't see it. What was that?
Driver programming.
Ah, excellent. Is when we program drivers. All right. So what does a driver do? It does. It does. Do we have to have a driver to make a device run and do what we want it to do? So why do we want a driver? Do what? Sometimes, but you know, the hardware is limited by its own design.
More universal interactivity.
Okay, because what I want is I want a driver is just a piece of software that takes requests and manipulates them in such a way that they can be understood by the specific hardware that that driver is a driver for. Okay, so our drivers can make it look like we have a consistent interface for all printers, when in fact behind the scenes the way data gets passed to the printer is defined by the engineers who designed that specific printer or any specific printer, right? And you'll also notice that in that role, drivers are all the time trying to communicate with external devices, okay? So drivers often have to exist in kernel mode, okay? So there are things that the operating system does to ensure that devices that go into kernel mode must be acting in a secure and reasonable way that will not be harming any of the other processes or the state of the computer itself. Okay, that's concurrency. It's one of the things we'll be talking about with concurrency, and one of the things we'll be talking about in security, the security component of the course. Okay. Questions about any of that? Yeah. So remember, the last kind of major topic I want to talk about is that I want to talk about the difference between graphical user interfaces and command line. Okay. I would expect, but could not guarantee, that you could have made it all the way to 420 in this degree program without seeing command lines. Like, I expect you have used a command line at some point, okay? But I can't guarantee that, right? So let's start with graphical user interfaces. All right, what does that mean?
User interface that might have buttons or
Okay.
Xboxes or something that you can work with.
Here's one. This is the graphical user interface that is here in Windows 10. That's the kind of the default graphical user interface for in 10. Have you ever thought about what it means to click this button? Okay. Have you ever really drilled down through all the layers of abstraction that are required for whatever's going to happen next when I click this button or any of these buttons over here, right? Have you ever thought about how this works and how the layers of abstraction are so very different here? Okay, because there's no a computer does not know what a icon is. Okay, there's no such thing as a file when we're talking about computers, right? They're just collections of bits. Okay, This image is just a file that is a collection of bits. And the act of clicking on this, right, is not really clicking on anything. It's just putting input into a program, the operating system, right, that then interprets that into something that the computer can do, run a program, for instance, okay? There's nothing sacrosanct or specific about this graphical user interface that makes this Windows, okay? This is just the default graphical user interface. In the Linux world, now in the Windows world and in the Mac world, they want to lock the user down into a set of user interfaces that are supposed to be designed to keep the user satisfied with the experience. Okay? But in the Linux world, there are hundreds of graphical user interfaces that you can choose from, regardless of which version of Linux, which distro of Linux you're using. In fact, one of the main things that makes a distro to the average Linux user is which graphical user interface are you using? Are you using GNOME? It's the one I always use. So I think the others are what, KDH, KDE, yeah. And who decides what graphical user interface you're going to use? The user. You can install one. They're all open source. Install the one you like. Get the little bobs and whistles where you want them. Okay? Make the images look like you want them to look. But why? Because the operating system doesn't care. Okay? Because the graphical user interface and the operating system are not the same thing. Right? Have you guys ever seen Microsoft Bob? This is going back a few years. I actually have a link to a YouTube video on today's notes, which I won't show for you, but I recommend you kind of look at it. It's really interesting. Melinda Gates, the first big project that she ran before she even married Bill Gates at Microsoft was Microsoft Bob. Microsoft Bob was a graphical user interface program that sat on top of Windows and got rid of the notion of a desktop. And when you logged into Windows, I think Windows 95, when you logged into Windows, you saw an image that looked kind of like this, right? Or the default one was actually just somebody's house. So this one. Okay, this is your login screen, right? It's like coming home. So to log in, you literally click on the door and it asks for your password. Okay, there's no icons on this. If you want to do finances, you go into the money box. Click on the money box, right? If you want to do internet, it's over here. Okay, this was just a separate graphical user interface, a different one for Windows. And I only mention it because it's interesting to show that the one default is not so heavily integrated into the operating system itself that it defines the operating system. No. What defines the operating system is much more in line with the other kind of typical user interface, the command line interface. Okay? Right? In Linux, in Ubuntu world, and really everywhere, we call this the terminal. Okay? So that's actually a really old term from back when computers and keyboards and monitors used to be connected over teletype lines to a central computer, right? And so what you were seeing in front of you was not the computer running software in front of you, but just a dummy terminal that was relaying what the computer in the closet down the hall was saying and taking commands from you, okay, back and forth, right? We can do something very similar, assuming, as I think it does, that these machines still have putty on them. Looks like maybe they don't. Well, anyway, I'm not going to spend time. We're coming close to the end of time. I'm not going to spend time looking at this right now, but I can log in to a machine over a text-based terminal that's down the hall. Okay, that's in somebody else's office somewhere else, and not have a graphical user interface and still use that operating system. And that, in fact, that's a thing that we're going to do. Okay, so one of the main components of any operating system is the shell. Okay, can I do this? Oh, also command prompt is what we call it inside Windows. Okay, but this is a terminal. Okay. Oh, dir/p. Y'all are stressing me out because I don't remember my Windows command line very much. I don't use Windows. But dir is directory/p page. Put up the directories that are inside DRay4, which is where we currently are. CD, I think it's / to go to root. Now we're in a different directory on the machine. dir/p. There's lots of things on the C drive. Okay, right? So I can move around in the files. I can open files. I can run programs. dir is a program. Okay, dir is one of the fundamental programs that the Windows operating system is composed of. Okay, and so one of the things that we're going to do later this week, and I've already planned this out, and I'm going to make a supplementary video about this. I think I mentioned it earlier, right? One of the things we're going to do is we're going to look at how to use the Linux shell. It's actually a OpenBSD shell, right? But a Linux type shell to access operating system commands, okay? And ultimately what we want to do is we want to write our own shell to show how shells work, okay? But I want to divorce you from the notion that the graphical user interface is the operating system, because they are not one and the same. In fact, the graphical user interface, if anything, is just laid on top of the operating system. Okay? The operating system, from our worldview, is not the abstraction of the graphical user interface. Instead, it is the specific software and the specific processes and functions that control the computer. And we can have more direct access to that than through the graphical user interface. Okay? Yeah, so the shell, you can actually do programming. It's called shell scripting, and maybe we'll talk about that here later this week. But for right now, that's fine. And the very last thing I want to talk to you about is system calls and supervisor calls. So a system call is a request from an application for an OS service. What kind of things are OS services? Network type things. Device, anytime I want to get a device. Memory, reading from disk, which is a device, right? Right? Those all represent OS services. So system calls are implemented as library functions. Okay, they can be directly called by a process running on that machine. So it's kind of like the notion of an API. Now, I won't say it is an API, an asynchronous programming interface, but it's the same notion, right? The API actually exists at least one level above this, but it's a function in a library that can be included in our code and reveals the operating system's system process. Okay? Reveals the operating system service. And so then a supervisor call is a privileged instruction that automatically transfers execution control to a well-defined location within the OS kernel. So this would be like a system call, but within kernel mode. Okay. So what's the benefit of having functions what's the benefit of revealing those operating system services through a function? Okay. I can do some validation inside the function, right? I can do some checking to make sure, right? It's the same, it's like a lower level concept of information hiding. Okay? Think back to 255 and 355. Okay, I don't know how long it's been for you guys. But why, when we're making C++ classes, do we have public and private attributes? Exactly. And in the same way, there's sensitive instructions, sensitive services that we don't want the outside world to be able to manipulate directly. Okay? So we reveal those through functions, and those functions can be designed in such a way that they allow us to check for illegal or illicit behavior before we actually run that in the kernel mode. Okay? Okay, so I didn't talk about everything that's in chapter 1. Okay? I covered most of the high points of chapter 1. Next week, we're going to move on to chapter 2. So what does that mean for you? That means that you are not only merely responsible for the things I have said in class, but you are also responsible for all the content in the reading. Okay? And just because I didn't say it in class doesn't mean it's not important or that it won't show up on a test or that you shouldn't understand it in general when you're trying to understand about operating systems. Okay? I know we get in the habit of, well, I'll just come to class, I'll listen to the professor, I will look at ESPN while the professor talks. His words will somehow manipulate the synapses in my brain, okay? At a later date, it'll just automatically make sense when we start to take an exam because of that synapse manipulation. Unfortunately, because we can't meet twice a week, that's definitely going to be a strained assertion. Right? I can't cover all the material in class with you in class, so you're responsible for the reading and for understanding the content in the reading. Okay? All right, so I'm done. It's time for you guys to go. I will say I won't put the recording up. Hopefully it's worked, fingers crossed. I won't put the recording up till the end of the week, but I will put it up at the end of the week. And additionally, as promised, there will be an assignment come out and a supplementary video that you need to watch concerning that assignment later this week. I say later this week because I haven't made it yet, but I think I'm gonna be able to get it out on either Wednesday or Thursday of this week. Okay. All right. If you have any questions, you know how to get in contact with me. Otherwise, I'll see you next week.